In this video, we're going to discuss the classical approach to calculating probability. And I want to put a big caveat to this approach. I commonly see students misuse this approach because they forget that this approach requires that all of the outcomes are equally likely. So let me write this down. Requires equally likely outcomes. Okay, so if the outcomes are all equally likely to occur, then you can use this approach, otherwise you cannot. All right, so let's see. What this approach says is that if you want to calculate the probability of an event A, then what you do is you can look into the sample space. You can see the number of ways A occurs. Okay, and then divide that by the number of events in the sample space. Number of events in sample space. Sample space. Okay, so this is actually why we talked about how to determine a sample space, was mostly so that we would be able to use this classical approach to probability. All right. Okay, so let's go ahead and let's start with this first example. Let's find the probability of flipping a head. Okay, so H is going to be flipping a head, the event of flipping a head. So flip a head. Okay, let's see, what is our sample space? Okay, sample space for flipping a head. Well, you flipped a coin. That's a procedure that you did. Okay, so I either get a head or I get a tail, right? So this is the sample space. Okay, so then if I'm trying to calculate the probability of getting a head, the number of ways a head can occur, well, it can occur one out of the number of events in the sample space. Well, there's two events in the sample space, so 1 out of the 2, which is 0.5. Right? So 50% of the time you get a head, which we all know that to be true. So there you go. This this classical approach to calculating probability works. However, if the coin were weighted, right? So meaning that the probability of getting a head or a tail, one of those was more likely than the other. If the coin were weighted, you could not use this approach to calculate the probability of getting a head, which is why it's so important that this approach requires equally likely outcomes. Okay, so don't forget that. Okay, let's do another example. So if a family has 3 children, find the probability that they will have 2 boys. All right, so let's think of our sample space. All right, I think we talked about this sample space earlier. So for the first child, I could have a boy or a girl. For second child, I could have a boy or a girl. All right, there are 2 possibilities here. There are 2 possibilities here. And then for the third child, I could also have a boy or girl. Boy or girl. Okay, so if I'm reading off my sample space, I'll start with B, 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 G, B, G, B, B, G, G. Okay, so that's the first part of the tree. Then I could have a girl, boy, boy, girl, boy, girl, 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 boy, and a girl, girl, girl. Okay, so 2 times 2 times 2 is 8. So there should be 8 possible outcomes, 8 events in the sample space, and looks like, if we count this up, we have 8, so that's good. Okay, so this is my sample space. All right, so I'm trying to calculate now the probability of having 2 boys. So if I'm going to define the event A to having 2 boys. Okay, so I'm trying to calculate the probability of A, the event A. Well, how many times in the sample space do you see 2 boys? So I'm going to say having exactly 2 boys, so not 3 boys, okay? So exactly 2 boys. So there's 2 boys here, 2 boys there, 2 boys there. All right. So it looks like three outcomes in the sample space have 2 boys. Okay. All right. Out of 8 possible events in the sample space. If you plug that into a calculator, you could leave it as a fraction, but you could also report it as a decimal. You get 3.75. Okay, so in other words, you could interpret that to mean that 37.5% of families that have 3 kids have exactly 2 boys.